Hi everyone, I'm Steve Brunton from the University of Washington, and I've been looking forward to making this video for years. Today I'm going to talk about how we can model very complex fluid dynamic systems using sparse nonlinear modeling techniques from machine learning. So this is one of my favorite topics, and this is an area of active research in my lab here at UW. And in 2016, we published a paper where we could build sparse nonlinear models from data of systems, and we looked at this simple laminar flow past a cylinder. This was our kind of big example in our 2016 paper. And so in this lecture, I'm going to tell you about what's happened in the last 5 years and some of the big strides we've made in extending this to much more complex fluid dynamic systems. So from one cylinder to this 3-cylinder configuration that has more broadband turbulence. We're looking at electroconvection systems. So this is a complex 3-way coupled device. We're looking at cavity flows. Okay, so really interesting, rich dynamics of this cavity flow. All the way up to spheromac fusion reactor simulations, we can build these sparse nonlinear models. Turbulent wake flows with our experimental collaborators in Europe. So very excited to walk you through some of the progress in sparse nonlinear models of fluid dynamics. In all of these cases, we are going to find models like this, x dot equals f of x, where x is a low-dimensional vector that describes the dominant coherent patterns in these flows. So out of the very complex millions or billions of degrees of freedom you would need to simulate these on a computer, we're going to extract the 3 or 4 or 5 most important coherent structures in X. And F is going to be the dynamics that describe how those coherent structures evolve and interact in time. And that's going to be a sparse, nonlinear dynamical systems model. So that's what we're going to do today, and I'm going to jump right in. So I want to acknowledge that this has been work with lots of great colleagues, co-authors, collaborators, great students and postdocs on this. So the sparse nonlinear modeling work started out with Nathan Kutz and Josh Proctor, where we developed lots of the mathematical theory and extensions of the algorithm. And then we've extended this to many fluid systems with Bernd Nowak, J.C. Loiseau from Paris Tech, George Regas from Imperial College. And I want to also acknowledge the Army and the Air Force funded most of this work. So, and all of this was done by our excellent students and postdocs on these projects. Okay, good. So I want to start off, I'm going to start off on my soapbox here. This is kind of my entry point when I talk about machine learning. So many of you have heard this before if you listen in and you've seen some of my talks. There is a need for interpretable and generalizable machine learning methods. So instead of, we know that neural networks are super powerful, but they're kind of opaque, they're black box. So we want machine learning models that are more interpretable and generalizable. And instead of defining these, I'm just going to make enemies if I try to define these things. I'm going to give you an analogy. Okay? So in my mind, the quintessential interpretable generalizable model is f equals ma. So it's interpretable because it has 3 terms, f, m, and a. They have units. I can write down these equations for a particular system of interest and analyze them, and we can discuss what those terms mean. It's interpretable. It's generalizable in the sense that Newton can learn f equals ma from apples falling on Earth, or so the story goes. And that same model is valid when we design space missions to land humans on the moon. Okay, that is a generalizable model. Now, I have no doubt that if I had movies of apples falling, I could train a deep neural network to make another movie of an apple falling, but that would not be useful to land humans on the moon. It wouldn't be generalizable in this way. This is the kind of model that we want in engineering sciences, in fluids especially, because so many of our applications of fluids are safety critical, like flight, and we can't afford to not understand our model, and we can't afford for it not to work in a regime where we didn't expect it to be. And this is not just Newton. This idea of kind of mathematical modeling being as simple as possible but not simpler is one of the cornerstones of mathematical physics. Einstein observed this. This was observed by Aristotle 2,000 years earlier. Occam, Pareto, you name it. Great minds have been adhering to this principle of parsimony or simplicity to get these kinds of models in physics. And so what that means for us today, mathematically, how we're going to use this in fluid dynamics, is we are going to build low-dimensional models in terms of only the few variables that matter, the coherent patterns in the flow. We're going to extract those low-dimensional representations, and we're going to build sparse dynamics models for how those low-dimensional patterns evolve in time together. Okay? And low-dimensional and sparse are the two mathematical ingredients that are going to give us interpretable and generalizable models in fluids. So sparse models on a low-dimensional state vector. So fast forward 300 years, and in the modern era, we see a great analog of this in the chaotic thermal convection problem, the Rayleigh-Benard convection. So this is a very cool fluids problem where you have a hot plate on the bottom and a cold plate on top. This is kind of a model for how the atmosphere convects when the sun hits the planes and the air starts to warm up and cause these large convection cells. And this fluid flow equation is what motivated Lorentz in 1963 to develop the famous Lorentz model. Now I'll point out, I've added the names Fetter and Hamilton. So this is Linda Fetter and Margaret Hamilton. They were his graduate students who helped him run these supercomputer simulations to generate the data he used to build his model. So I think it's important to remember their contribution. That's the Margaret Hamilton of NASA fame. So she went on to do many, many great things. And what Lorentz was able to do was take this very complex fluid flow field and distill it down into these three equations you see on the right. And you'll notice that this has exactly the low-dimensional and sparse nature that we talked about before. So it's low-dimensional in the sense that Lorentz is characterizing this system with three variables, x, y, and z, that describe three spatial modes that you can add up to approximate this flow field. And those modes were posited earlier by Saltzman at Yale. And it's sparse in the sense that on the right-hand side, out of all of the possible things that could be in the dynamics, there's only 7 terms. Okay, so it's sparse. The interactions of x, y, and z are simple, and there's key mechanisms where they interact through sigma y and minus sigma x and things like that. So that's going to be kind of this key theme, is building these low-dimensional sparse models. And we're going to do this in an automated way. So what I'm going to show you today is how we are automating what Lorentz did in 1963 for more complex flows today with machine learning and with data. Okay, so this is the sparse identification of nonlinear dynamics algorithm, or SINDy. This is the 2016 paper I was talking about with Nathan Kutz and Josh Proctor. And I'm going to walk you through this on the Lorentz system. So imagine that we have the Lorentz system, and I'm simulating data, but all I have access to is the data. I don't have access to the equations. So I measure x, y, and z in time. So I've got a time series of these measurements. And I compute x dot, y dot, and z dot. They're time derivatives. So I don't know the equations, but I do have data. Now, the simplest thing you might think of to do is to build a linear regression model, a best fit model, that tries to fit x dot, y dot, and z dot in terms of a linear model A times x, y, and z. This is exactly what dynamic mode decomposition, or DMD, does. Now we know that a DMD model, this is a 3x3 linear model with a single fixed point at the origin. There's no way it can capture this rich complexity of the Lorentz system with multiple fixed points, unstable periodic orbits, and chaos. So instead, what we do is we augment the right-hand side with more candidate terms in the dynamics. So instead of just linear terms x, y, and z, we add x squared and xy, y squared, yz, all the way up to, in this case, 5th order polynomials z to the 5th. And all of these gray columns, I can actually build those from the data I collected in x, y, and z. And now the trick is, we're trying to find the fewest columns. Remember, we want sparse models. the fewest columns of theta that add up to equal x dot, that add up to equal y dot, and that add up to equal z dot. And when you do this, you uncover, it turns out that the fewest columns that add up to equal x dot, y dot, and z dot highlight the original terms that were in the dynamics that actually generated this data. Now, this is nonlinear system ID. We're generating these models directly from our data, even though we've never seen the equations before. So the sparse optimization, if you had asked me 20 years ago if this is possible, I would have said no. This is a brute force combinatorial search. But it turns out that now this is pretty much a commodity algorithm in statistics to find these sparse linear combinations. So there's dozens of algorithms to compute these things and to find these sparse representations if you build your library correctly. Now, I'll point out, in this case, we assumed that we knew the right measurement variables, x, y, and z. And that's a huge assumption that I'll come back to later. OK, good. If you're interested in trying this, we have open source software called SINDy in Python. And you can download this on the GitHub and read about it in the Journal of Open Source Software. Good. So we don't just have to build ordinary differential equation models. And here we're going to start thinking about fluids again. We can build partial differential equation models. So this is great work by Sam Rudy, who is a PhD student working with Nathan and me, where he collected full spatial temporal flow fields for the fluid flow past a cylinder. And instead of building just an ordinary differential equation problem, he builds a library of partial derivatives and nonlinear products of partial derivatives. And when he applies the same SINDy sparse regression procedure, you essentially find the sparsest model that's consistent with the data are the Navier-Stokes equations here. And you'll notice that these pink terms are the 1 over Reynolds number. They're within 1% of the true value. So pretty remarkable. Just from data, by applying this sparse regression, you learn the Navier-Stokes equations using sparse regression. Now, because the spatial temporal data is so rich, there's so much of it, we can dramatically subsample the data. We can measure at a few random locations in space and time. And even on that sparse subsampled data, we can still identify the same Navier-Stokes dynamics. So this is pretty cool. OK, good. Now, I told you earlier that we assumed that we knew the right coordinates x, y, and z for Lorentz. So there was some really important work by Kathleen Champion. This was also when she was doing her PhD with Nathan and me, where she essentially combined the idea of a deep autoencoder network from machine learning and our sparse SINDy models that I was just showing you. And so the autoencoder learns a coordinate transformation where your dynamics become sparse in the latent variable z. And so this is a simultaneous discovery of coordinates and of sparse dynamics. So really cool work here. And Kathleen actually has a great video lecture on this that I'll link below. So you can read all about this and see her lecture. OK, good. So now I really want to dive into how we're using this in the field of fluid mechanics. OK, so I'm going to go through vignettes of how we're doing sparse nonlinear modeling to get reduced order models of complex fluid flows. So this reduced order modeling paradigm, again, I'm going to walk you through what we started doing in our original 2016 paper and build from there. So this is our simple low Reynolds number flow past a cylinder. This is a canonical example of vortex shedding. And Bernd Nowak and collaborators in this famous 2003 JFM paper told us the right coordinate system, the right low dimensional variables to measure this, this flow in. So the first two proper orthogonal decomposition modes or singular value decomposition modes, and this third shift mode, which is the unstable steady state minus the mean flow. And if you measure the flow past a cylinder in these three coordinates, you can write down a very simple nonlinear quadratic model here in blue that gives rise to the transient and steady state behavior of this system. This is a famous paper, and it was famous because it wrote down such a simple model for this flow using kind of simple arguments. And this dynamical system in blue gives rise to a slow manifold, and it's very kind of interpretable, sparse, and low dimensional. And so this is going to be the example we're going to warm up and try SINDy on to get a sparse model. So we are going to measure this system in those same 3 coordinates, and we're going to take x, y, and z and feed those into our SINDy algorithm. And when we do that, we uncover a model that has essentially the same terms as the NOAC model, and it has the same slow manifold. Our identified system has the slow parabolic manifold, and it captures the same transient and steady state dynamics as the original NOAC model. So this is pretty cool. We were really excited when we saw this. Very soon after putting this paper on the archive, I got an email from Jean-Christophe Loiseau. He was at KTH at the time. Now he's at Paris Tech. And he had 2 key innovations that really upped our game in modeling fluids with SINDy. So the first observation is that when we do this sparse SINDy regression, we're not taking into account any background knowledge about our flow. But JC knows that incompressible Navier-Stokes equations conserve energy. And he says they conserve energy. We know how they conserve energy through these skew-symmetric quadratic nonlinearities. And so in our sparse regression, you can essentially add constraint equations so that the quadratic terms have to be skew-symmetric. And by doing so, we make it so that our models, our sparse models, conserve energy by construction. So that immediately improves the stability and the learning rate of our models. The second thing he did, and this is, I think, really important, is include higher order nonlinearities into the model. So in our original model, we had quadratic nonlinearities because we wanted to match Barrett-Noack's model, and we knew that the Navier-Stokes equations had quadratic nonlinearities. But when you allow yourself to have higher order terms, cubic, quintic, septic, nonic, so 3rd, 5th, 7th, 9th order terms, you essentially are accounting for very low energy modes that we've truncated or neglected, and how they affect the large energetic modes we are trying to model. So by adding cubic and 5th and 7th order terms to these x and y equations, we essentially account for these higher frequency mode pairs that we have neglected, these low energy but high frequency mode pairs. And so what you get are much more accurate models, and it's in some sense a rudimentary closure model for this very simple laminar flow. So I want to be careful in calling this a closure model because this is not turbulent, but it is kind of closing the truncated scales and how they affect the large energy scales. So let's see how this works on the cylinder flow and on the cavity flow, 2 of my favorite examples. What we see here in the middle column is kind of our benchmark. A delta is a quantity that's essentially a proxy for the drag. So this is a quantity of interest we want to model in the system. And the white curve is the ground truth from a direct numerical simulation. So when we start off the simulation, the drag rises, and it goes to some steady state value. And in yellow and in blue, these are the industry standard, state-of-the-art POD Galerkin models. We basically take the proper orthogonal decomposition, and we Galerkin project the Navier-Stokes equations onto either 3 modes or 7 modes. So we see that these models, and these are the kinds of models Barrett-Noack was building in that 2003 paper. So we see that these are qualitatively pretty, they capture the right features, but quantitatively they're off. They have the wrong rise time, they overshoot, and they have steady state error. Whereas when we introduce our SINDy models with either cubic nonlinearities or constraints built in, we almost perfectly capture both qualitatively and quantitatively the dynamics. Now, here's a really important point I want to make. Because these SINDy models are sparse, it's literally a sparse differential equation with as few terms as possible, it is interpretable. JC and I can write down this equation and go get a coffee in Paris and manipulate and analyze that equation. And that's exactly what he did. And he wrote down this differential equation from the SINDy model for cylinder flow and showed that this system is essentially a spring mass damper with a nonlinear damping term, or a van der Pol oscillator. And this is, to date, the simplest and the most accurate model of the cylinder flow that I have seen on record because of sparsity, because of the sparse regression. Okay, good. Now, we have extended this to more complex flows, like this fluidic pinball that has 3 cylinders and has much more broadband behavior in the wake. And importantly, we don't need the full flow field or someone to tell us what coordinates to measure this system in. We can build our sparse models directly from lift and drag measurements of these 3 cylinders. So those are kind of obvious measurements you would take. You don't need the full wake velocity field measurements. You just need 6 measurements of the lift and drag on each cylinder, and you can build these very, very accurate SINDy models that match the DNS, the direct numerical simulation, very faithfully. So I think this is super cool. This accounts for some of the issues of, proper orthogonal decomposition often is going to fail if you change the flow velocity, or I change the geometry, or I move the bodies. But building models directly in lift and drag coordinates is really nice because those are intrinsic, and those mean the same thing even when my flow velocity changes, even when my geometry changes. Okay, good. So now we're going to go on to some more complex examples. So I'm going to go back to the chaotic thermal convection Rayleigh-Benard. And I want to highlight this really cool work by JC that he put out last year in TCFD, where he was analyzing this chaotic thermosiphon. So it's basically a hula hoop or an annular region that's heated from below and cooled from above. And it creates and sets up this thermal convection cycle that's chaotic, similar to the Rayleigh-Benard convection. And so what JC was able to do by extracting modes automatically through dynamic mode decomposition and modeling the evolution of those modes in time with SINDy, he was able to show that this chaotic thermosiphon flow is structurally the same as the Lorentz 63 model for Rayleigh-Benard convection for a completely different geometry. And so this is a really, really cool result, very nice paper, kind of showing that Lorentz is even more general than we thought to these other flows, and that you can automatically model them using these techniques. So that model was not written down for this before JC, and so this is a real new scientific discovery. Very cool. We've been working on other convection problems. So this is work by Yifei Guan and Igor Novosilov. Yifei was a PhD student working with Igor. He's now a postdoc at Rice. And he was working on this great electroconvection problem. So electroconvection is a little bit more complicated than standard Rayleigh-Benard because it has a 3-way coupling between the fluid flow, the charge density, and the electric field, which sets up these rich kind of chaotic convection patterns. And so what we did here is started trying to apply these automated sparse modeling procedures to get low-order models of this chaotic electroconvection. So we collect spatial temporal data in time, in space and time. We extract the key modes, the low-dimensional features, the energetic coherent structures that matter using proper orthogonal decomposition. And then we look at how the amplitudes of those POD modes evolve in time. So A1 is the amplitude of the first mode, A2 is the amplitude of the second mode, and so on. And these are how the mode amplitudes evolve with respect to each other in time. And we noticed that this flow has deep, deep symmetries. There is an incredible symmetry when you look at these mode coefficients of how the energy is being transferred through these modes. And so we were able to learn those symmetries, to write them down, and to enforce them in our SINDy model. So this is using that same technique Jean-Christophe Loiseau taught us. We can now add those symmetry constraints directly into our SINDy model, so we get a nonlinear model that it satisfies those symmetries by construction. And we get this sparse model that has the same skeletal kind of structural dynamics. It misses some of the details, but it captures the big features of this flow very nicely using this. And we can get the flow fields by adding up these POD modes in these A1, A2, A3 combination. So let's zoom in a little more and look at these symmetries. So this is the phase portrait of those POD amplitudes. And we can write down these 5 symmetries that we observe in the system. It's invariant to switching the sign of A2 or switching the sign of A3, and so on and so forth. There's these invariants in the data. And so what that means is that when we write down our SINDy library, the library of possible nonlinear terms in the dynamics, a lot of them immediately have to be 0. We've blacked out a lot of these terms that can't be active with these symmetries being observed. And even more than that, there are other conditions, like this sigma 2 has to be the opposite of this sigma 2, and so on and so forth. There are these kind of additional constraints on the SINDy library that have to be true based on these symmetries. And so when we enforce those in our SINDy regression, we can get away with less data because there's less coefficients we're trying to identify, and we get more stable, more accurate models. In this case, again, we get this model here that has the right structure of the data. Now, it doesn't capture every small feature. There are these little loops here we're not capturing. But we get a lot of the features of the data in kind of this chaotic electroconvection. So very promising that you can scale this up to pretty sophisticated systems. Again, we didn't have reduced order models for this when we started. This is a new model. And you can analyze this kind of how Lorentz analyzed the 63 model. So another great example, this is work by Alan Kaptanoglu, who's a PhD student working with me on plasma physics. So he has a 3-dimensional simulation of a spheromac fusion reactor here that is matched to experiments. And he has, from this simulation data of this 3D system, extracted, again, the low-dimensional features we care about using POD. And he had to cook up his own dimensional POD since your magnetic field and your velocity field have different units. So we had to make a conversion so they can speak the same language. And then in this coordinate system, you're able to build a sparse nonlinear model that satisfies the constraints of the PD, of the MHD equations. And down here, you see that our reduced order model, our sparse nonlinear model, captures the structural dynamics of this spheromac fusion reactor very, very accurately. So this is very promising. We're starting to add things like injector dynamics and control so that we can use these reduced order models for online control of experiments, hopefully. So that's where this is going, is these models are so fast and so efficient, and they seem to be pretty accurate. Maybe we can use this for something like model predictive control down the road. OK, good. So I'm just going to keep going because I love this stuff, and we've got more. I've been kind of blown away with the progress in the last few years. If you had asked me 2 years ago if some of these flows were possible to analyze with SINDy, I would have said probably not. But with great students and great collaborators, we've started opening up a lot of these problems and complexities. So one of the ones I'm really excited about, this is new work by Jared Callahan, a great PhD student of mine, and J.C. Loiseau. The archive paper should be coming out very soon, where we're analyzing more complex, higher dimensional systems like this shear-driven cavity that has, if you did the proper orthogonal decomposition, you would find that there might be a couple dozen modes that are energetic and important. And so when they analyze this flow, of course, you have the shear layer instability, and you have the inner cavity modes. Like, this is classical theory. We know that these are dominant kind of mode structures that give rise to these dynamics. But in a purely data-driven fashion, again, when we look at the mode amplitudes versus each other in time, so A1 versus A2, A2 versus A3, and so on, you see this incredibly rich correlated structure here that's highly indicative of nonlinear dynamics. And so by identifying the 2 driving mode pairs, Jared and JC were able to build this extremely simple SINDy model up to 5th order that almost perfectly captures the dynamics of the full nonlinear simulation. And if we zoom in, we can look at the power spectrum of the log of the energy. And we have power peaks from the cavity mode and the shear layer mode. We have power peaks from kind of these harmonics, the second harmonic, the nonlinear crosstalk, and higher order harmonics. And our SINDy model almost perfectly captures all of them. This blew me away when I saw this. Absolute beautiful agreement of many, many modes, all the way up to like A19 in this case. That's the 19th POD mode. So we're capturing the full spectrum of this cavity, again, with a 2-state SINDy model, and then kind of how they impact these higher modes. Very cool. You can read about this soon on the archive. And another thing kind of I'm really excited about that I wouldn't have thought is possible a couple of years ago is extending this to full-blown turbulence systems. So turbulence is hard because you have coherent structures, but they're forced by multi-scale structures that you don't want to model or necessarily kind of keep track of. And so this is work by Jared, JC, and George Regas, where we essentially are modeling the Langevin dynamics of turbulent fluid flows. So here we have x dot equals f of x. That's our original SINDy model for the coherent structures, plus sigma w. This is a noise term, a colored noise term that forces our dynamics stochastically. And so what we're doing here is we're simultaneously identifying the sparse nonlinear dynamics of the coherent structures and the colored noise forcing of all of those small scale turbulence fluctuations that are forcing the system. This is closely related to the Fokker-Planck equation, which describes the evolution of distributions or ensembles of trajectories, but we're taking the Langevin approach. And I'll point out, we're building on prior work by Bonasega and Clementi and others that extended SINDy to Langevin systems for molecular dynamics. So we've extended it to higher dimensional fluid systems. And I'm not going to jump into all of the details here because it's a little bit involved, but the basic idea is that we're parametrizing our nonlinear dynamics and our noise, just like in SINDy, and then we're finding sparse nonlinear models by fitting the data, by essentially building distributions and by adjoint optimization trying to find sparse Xi vectors that model these nonlinear dynamics and noise forcing. And in all of the cases we've looked at, from simple toy examples to fully turbulent wake data from experiments, we get very simple structural models for the coherent structures and a very simple representation of the colored noise forcing from the subscale turbulent fluctuations that we're not modeling or we're not keeping track of. And just to illustrate this on the cavity flow, this again is the full direct numerical simulation. And down here, this is our Langevin reduced order model. So you can see that we're capturing kind of the key dynamics of these POD modes, these kind of figure 8 dynamics, but we're also getting the spread of the dynamics because we're accounting for this noise forcing that broadens those trajectories. Very, very cool. And it seems to work on this fairly turbulent, sorry, not this, but on really turbulent data like wake data from experiments. OK, good. So I think the last thing I want to show you, I've shown you a lot. This is a whirlwind tour of sparse nonlinear modeling of fluids. The last thing I want to show you is pretty new, and it's a little bit of a different take on sparse modeling. Again, with Jared Callahan, James Koch, Nathan Kutz, and Bing Brunton. And this is sparse modeling of terms in equations to see which terms balance each other at what locations of space and time. So there's this idea of dominant balance in physics, where even if you have a very complex equation, like the full 3D Navier-Stokes equations, maybe at a location in space, only a few of those terms are active and large and are kind of balancing each other out, while most of the other terms are small. So this is the idea of dominant balance, and it's the foundation of asymptotic analysis and asymptotic expansions. Most of the applied math departments in the country grew up out of this idea of asymptotics and dominant balance in physics, where you could write down solutions on pen and paper by hand before computers by simplifying the equations to a few key terms that are interacting. And what Jared's going to do on this Johns Hopkins turbulent boundary layer is automate this dominant balance procedure with machine learning and sparse nonlinear modeling. So if you take the Reynolds average Navier-Stokes equations, the RANS equations here, you see that there are, in 2 dimensions, there are 6 terms. And for each of those terms, you can essentially plot what that term's magnitude is at every point in space. So this is one term in my equation at every location in space on the boundary layer. And you can plot all 6 of those equation terms like this. So this is essentially an equation space representation. So now for every point, I can take that point and I can plot it in a 6-dimensional equation space in all of these 6 coordinate axes. And that's exactly what Jared did. So this is just 2 slices in equation space of all of those points. And you'll see that the data appears to live on these kind of subspaces or clusters. So Jared applies relatively simple machine learning clustering, in this case Gaussian mixture models, to find which clusters are active, how the data clusters. And I'm only showing you a couple slices, so there's other dimensions where the other terms cluster. And again, dominant balance is about trying to figure out which terms are small, almost 0, and which terms are big and are balancing each other. So what we're going to try to do, for example, this red set of points here, this red cluster, this term is approximately 0, and these 2 terms are in a balance. So we're also going to apply sparse subspace identification, or sparse PCA, to find which terms are active, approximately active, and which terms are approximately 0 for each of these 5 clusters. And so again, these black squares are the terms that are approximately 0. And what's really cool is that every point here, you can replot that point in space, where it was in space, and you find that these 5 regimes of dominant balance correspond to 5 classical regimes from the boundary layer. So we recover the viscous sublayer, the inertial sublayer, the transitional region, purely in an automated, data-driven fashion. So this is phenomenal. This allows us to actually uncover these dominant balance regimes purely from data with relatively simple sparse modeling, right? We're trying to find the sparsest combination of terms that are active in these clusters. And again, this recapitulates classic boundary layer theory that was hard fought over the last 100 years by many, many smart people. So we've looked at this for the boundary layer I just showed you. We've looked at this for the super continuum laser, this high energy optical pulse propagation. This is a really cool example because this is a very nonlinear system. This is nonlinear wave physics. But it turns out when you do this dominant balance, the only region in the XT diagram where nonlinear terms are active is in this tiny thin blue layer here. So all of the nonlinearity is actually very localized in this problem. We've applied this to geophysical flows like the flow in the Gulf of Mexico from the HICOM data, and we've relearned kind of the classic geostrophic balances. And we're hoping to learn new balance laws, new almost invariances in the flow that might have been missed by humans, that might have been too complicated to write down. We're applying this to neuroscience data. And the real promise here is to apply this to fields where we don't know the answer, where we don't know about the transitional region and the inertial sublayer. Problems like neuroscience, where we can learn new dominant balance laws and simplified physics in different regions of space and time. So I'm super, super excited about that. And I hope you are too. I hope you use this for your own problems. I hope you extend the method and apply this to new problems to discover new models that we didn't have before. So I'm super excited about where this is, and I'm looking forward to making another video in 5 years, what sparse nonlinear models we have in 2025 or 2026. All right, thank you.